All right, so now we're going to go over the second problem for the water supply. So that's this problem here. It reads that a facility receives water at an elevation of 350 feet at the water meter and is 4.1 miles from the water tower. Just do this real quick, see if this helps. All right, the water level in the tower is at 527 feet, so all this is pretty important information. So that's your distribution elevation. Your supply elevation is 527 feet. The water flows at a rate of 110 gallons per minute. Assume it's an 8-inch diameter ductile or cast iron pipe. And it's all flange fittings, and these are your fittings. Okay, so we're going to find the total dynamic head and actual water pressure at the meter of this facility. So remember, dynamic head, we need to first do static head. So to even get to the dynamic head, you need static head, then you need your head loss, and that gets you your dynamic head is static head minus your head loss. All right, and then your actual pressure is equal to dynamic head divided by 2.31. So this is just our process for how we're going to do all this. And then, so that's what we've been doing so far. This problem takes it a little further because we then have to go into the actual house and make sure that the faucet, like up on the second floor, is going to be receiving enough water pressure. And then there's another problem we're going to go over here. All right, so on a separate sheet of paper, let's start copying this problem down. So number 2, part A. First of all, we need the static pressure or static head. And that's, remember, the supply elevation minus the distribution elevation. So we have 527 feet minus 350 feet is equal to 527 minus 350. It's 177 feet. Then you need to do your head loss. So we know we have 4.1 miles times 5,280 feet per mile is 4.1 times 5,280, 21,648 feet. And then you need to do all your fittings. All right. So again, when you do your fittings, you need to go to this table here, your flanged fittings table, right? Because all our flange fittings, and we have 8-inch right here. And then for this problem, we have cast iron. So our typical design value for Hazen-Williams constant is going to be 100. All right, so all that is where we're getting that information from. So again, try to remember that we have 2 90-degree elbows, 2 gate valves. So 90-degree elbow, when you look that up, (90-degree elbow). Oops, down here, 90-degree elbow, 8-inch. That's 12 feet for each one of those. So that's 12 feet times 2 is 24 feet. Let's see. Next, we have gate valves. And looking up our table here, valves down here, gate for an 8-inch, you have 3.2 feet. And 2 of those makes it 6.4 feet. All right, let's keep going. So line flow tees for an 8-inch. Look, tees, line flow, 8-inch, 4.7 feet. All right, so 4.7. And they said we had 17 of those, so calculate 4.7 times 17 is 79.9 feet. Let's see, we have so 6 branch flow T's. So an 8-inch flange branch flow T is 24 feet. And we have 6 of those. 24 times 6 is 144 feet. And then we have a swing check valve. Swing check valve. Make sure you look under the little fold in the crease in the paper. That's might be where it is. That's 90 feet. We only have one of those, so that's 90 feet. Add up all of these distances together. All right, so you have 21,648 plus 24 plus 6.4 plus 79.9 plus 144 plus 90. So that's 21,992.3 feet. So Hayes and Williams' formula is, remember, 10.44 times that length, 21,992.3 feet, times the flow rate, Q, or remember, I'll just write it out here. H sub F is equal to 10.44 times L times Q to the power of 1.85 over C to the power of 1.85 times D to the power of 4.8655. All right. So Q is the flow rate. That's 110 gallons per minute in this problem to the power of 1.85. All that divided by, let's see, C for this kind of pipe, like I said before, the Hayes-Williams constant is 100 to the power of 1.85. And then 8 inches is the diameter of the pipe to the power of 4.8655. All right, so I'm going to be really a little bit more careful here when I show you how to type this into the calculator, because I think I kind of rushed through it last time. So when you type in the calculator, it's going to be all the stuff in the numerator. So 10.44 times 21,992.3 times 110 to the power of 1.85. Remember, that's the caret right there. The denominator, you do need to be careful, mostly because of this exponent, and then immediately you have a multiply by another thing. So you definitely need to put in parentheses. So it's 2 sets of parentheses here. One open for the denominator in general, then parentheses 100 caret 1.85, and then what I missed or did incorrectly the first time, my first video, is you have to close a parentheses, then multiply by 8 caret 4.8655, close 2 parentheses. All right, it's really important that you put these parentheses in, because otherwise it'll do the 1.85 times 8 to this power of 4.65, and that'll be wrong. It's the 100 to that power. All right, so be careful with this. All right, so let's go ahead and type that in. So open parentheses. Let me raise this all up a little bit. Open parentheses, 10.44 times 21,992.3 times 110 to the power of 1.85, close parentheses, divided by open 2 parentheses, 100 to the power of 1.85, close parentheses, times open new parenthesis, 8 to the power of 4.8655, close 2 parentheses. All right, you do all of that, and you should get 11.055. And we can just say 11.06 feet. All right, so now we finally have the dynamic head, is the static head minus the head loss. So we have 177 feet minus 11.06 feet is 177 minus 11.06. We should have 165.94 feet. And so the actual pressure is equal to 165.94 divided by 2.31. So 165.94 feet divided by 2.31 feet per PSI is 71.8. The hundredth is a little irrelevant, but just not PSI anymore, or feet anymore, it's PSI. All right, so this is a really good pressure, remember, because you want it anywhere between 40 and 80 PSI. So 71.8 is definitely good. It's up on the upper end. Really good pressure. Okay. So that's part A. And now we're going to need to move into part B. So part B says, what is the static head at a sink on the second floor if the sink faucet elevation is 14 feet above the meter elevation? Again, you have to go all the way back to static head only depends on elevation. So you have to go all the way back to calculating static head and then go through this process again. All right. So, it's not saying. So, okay, it's asking the static head. So when there's no water movement, let's just draw a quick picture of this just to make sure we understand. All right. So remember, here's our water tower somewhere. Here's our house somewhere else. And the water line comes out here, comes over to the house, and it usually comes into the house like in a basement or like kind of in a, if you have a, so like, let's say that that's the ground level and here's the basement, or you have it either in the basement or in a crawl space or something. It comes in underground. All right. So this is the source elevation, and this is the discharge. Well, now we have a faucet up here, and so the water has to come up to this faucet. And you see now the water has to go vertically up somehow, and so it's losing head. All right. So remember the static head here, we said was 177 feet. Well, it's got to go now up 14 feet. So now the new static head is 177 feet minus 14 feet. 177 minus 14 is 163 feet. All right, so there's less static head up at this faucet. Okay, so now if we go into a little bit more detail, what's the water supply line from the meter to the house up to the second floor? So now we're talking about what's going on specifically with this line going up from here to the faucet. So it's 1-inch copper. It's screw fittings. And we have, it's 75 feet of pipe. It includes 4 line flow tees, a swing check valve, 7 90-degree elbows. All right, and the flow rate Q is 10 gallons per minute. Okay, so if you go back to all your Hayes and Williams stuff here, so now for copper, Hayes and Williams constant is 130. So I'll make that over, just do that over here. So C is equal to 130 now. Q is equal to 10 gallons per minute. And diameter is equal to 1 inch. And now for H sub F, we have 75 feet. For a 1 inch, remember I have screw fittings now, so 1 inch. Let's see, we had line flow tees. Line flow 1 inch, that's 3.2 feet. Times 4, 3.2 times 4 is 12.8 feet. A swing check valve, a 1 inch swing check valve is 11 feet. 90-degree elbow, 1 inch is 5.2 feet. So 5.2 times 7 is 36.4 feet. All right. And so that should be it. So add those up. You get 75 plus 12.8 plus 11 plus 36.4. And we got 135.2 feet. Okay, so now the head loss once you get in the house is 10.44 times 135.2 feet times Q, which is 10 to the power of 1.85 over Hazen-Williams constant for copper. It's 130 to the power of 1.85 times the diameter, which is 1 to the power of 4.8655. One good thing about this, using 1 inch pipe, 1 to any power is just 1, so you don't even really actually need to worry about this in the calculation, just thinking mathematically. So don't need to worry about the parentheses that I was talking about before with this specific calculation. All right, open parentheses, 10.44 times 135.2 times 10 raised to the power of 1.85, close parentheses, divided by open parentheses, 130, raised to the power of 1.85, close parentheses, done. 12.27 feet. We lost, inside the house, we lost 12 feet ahead. And if you think about it, the entire 4.1 miles from the water tower to the house, we only lost 11 feet of head. So it kind of shows you that with larger diameter pipes, you lose a lot less head, whereas inside the house, you can actually lose, or inside of a building, you can lose a significant amount of head if you're going up a few floors. All right. So when we're doing this is just inside the house. We need to go total HF. So that was taking into account the 11.06 feet from outside the house, plus the 12.27 feet from inside the house. 11.06 plus 12.27. You get 23.33 feet of head loss. All right. So remember, dynamic head is equal to static head minus head loss. So 163 feet was our static head, minus now 23.33 feet of head loss. 163 minus 23.33. We get 139.67 feet of head at the faucet. And so the actual pressure at the faucet, remember, is 139.67 feet divided by 2.31 feet per PSI. Running a little bit to the bottom here. So divide that by 2.31. And you get 60.46 PSI, which again is really good pressure. All right. Not the 70, was it 71 we had before, but still really good pressure even on the second floor. All right. So that's a review of how to do the second problem. And from here, we're going to go on with some practice problems. We have just some static head problems, some static pressure. So just the concept of, well, doing dynamic pressure, you can just do static pressure as well. Then we have actual water pressure and equivalent lengths on through. All right, so that'll be split across a couple days.